Welcome, Math 107 students, to lesson number 20, quadratic functions. We'll take a look at the preview exercises in this video. The general form, let's underline that or highlight it. The general form of a quadratic function is any function of the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a does not equal 0. It is different from a linear function because it contains an x squared term. The graph of any quadratic function is called a parabola, a U-shaped graph that opens either upward or downward. This form of a quadratic function, the ax squared plus bx plus c form, is one that you're familiar with. You're used to seeing it as y equals ax squared plus bx plus c. Okay, but now we're dealing with functions, so it will be f of x or g of x or h of x. And each one of these parts of the general form is called a term because they're separated by either addition or subtraction. And each one of these boxes or terms has a name. So the ax squared term, which makes this a quadratic, is referred to as the quadratic term. And that always has to be present. A has to have a value other than 0. The bx term is called the linear term. B can have the value of any real number, including 0. And c is the constant term. And c can be any real number as well, including 0. So let's take a look at how we're going to take this form of a quadratic and transform it into another type of equation that's going to give us some information that's helpful for graphing quadratics. So we learned when we studied transformations that the parent function for quadratics was f of x equals x squared. And we know that the point 0, 0 is called the vertex of this function. So graph the function g of x equals 2 times the quantity x minus 1 squared minus 3 by transforming the graph of our parent function f of x equals x squared. So with all of our work on transformations, we're going to take a couple of these key points that lie on x squared, f of x equals x squared, and use our transformations to find some points on our new function g of x. Okay, so we know that when we want to transform a function, we have to do all of our shape changes first. And in this case, we only have one shape change, and that's a vertical stretch by a factor of 2. Which says take all your y values on your original function and double them. So let's do that. Let's take all our y values and double them. So I have negative 3, 9 becomes negative 3, 18. And I'll just go down and take each one of these points and double the output of the y value. Hopefully, they're all correct. Okay, so we've done our shape changes. Okay, so if we wanted to, we could take this point and move it up to 18 and this point and move it up to negative 2, 8. But let's wait until we get all of our transformations done. So I'm going to erase that to give us a little more space here. So we've taken care of our vertical stretch. Next, we want to deal with any of our horizontal or vertical stretches. And it doesn't matter which one we do first, but let's take a look at what each of these, sorry for the distraction here. I have to get my pen working. There we go. So we notice that we have a horizontal shift going on that says shift to the right 1 unit. Since this is pre-operation, it's inside our function. Our pre-operation here, the operation of squaring, is our horizontal movement. And then outside of our squaring or post operation, we're going to decrease, excuse me, all of our y values by 3. So we're going to shift down 3 units. So this says I'm going to add 1 to my x values and subtract 3 from my y values. So let's do that both of those steps together. So we're going to take our x values and add 1 to them because we're going to shift them to the right. And we're going to take our y values and subtract 3 from them. So this first point here, negative 318, will become negative 2, 15. So I'm going to perform those two operations on the remaining points. So add 1, negative 1, 5. Okay, so these are my new points. So if I were to graph these points, these new points, I'd be at negative 2, 15, which would be approximately right there. Negative 1, 5, which would be approximately right here. 0, negative 1, there. 1, negative 3. 2, negative 1. 3, 5. And 4, 15. So let's use a different color. And here's our new function, g of x. So let's take a look at what happened to our vertex here. Our vertex on our parent function was 0, 0. And where did it end up going? Well, let's take a look at that. It ended up moving 1 spot to the right, shifting 1 spot to the right, and then down 3 units. Down 3 units. So our new vertex is at 1, negative 3. 1, negative 3. So the question we want to ask ourselves is, could we have identified the coordinates of the vertex of this transform function, g of x, just by looking at this equation? Well, if we notice that the subtraction of 3 from 0, the downward movement gives us our y coordinate, and then the shift right 1 unit gives us our x coordinate. We can see that by looking at this form of our equation, which is not polynomial, because we've got this 2 times the quantity x minus 1 squared minus 3. Notice we don't have this in the ax squared plus bx plus c form. There's multiplication going on right here, and there's subtraction. So we don't have it in polynomial form. We have it in a different form. But this form, we can look at it and pluck off the coordinates for our vertex. That's kind of cool. So notice here that the y value has the same sign. The sign of the y value is the operation that precedes it. In this case, subtraction becomes a negative. But just like we had to get used to with our horizontal shifts, we don't have a negative 1 here for our x coordinate. It's a 1 because this is being shifted to the right 1 unit. So we just have to remember those horizontal movements are always a little bit opposite of what we normally intuitively think. So what role does the y-axis, x equals 0, play in the role of f of x? Well, if you recall, y equals 0 is the line of symmetry for this parabola. We can fold this parabola around the y-axis, and each point to the left of the y-axis has a matching point to the same distance to the right of the y-axis. And similarly, now our new function here, g of x, if we drop a vertical line straight down through x equals 1, we have a line of symmetry as well. So the line x equals 0 is the line of symmetry for the graph of f, and the line x equals 1 is the line of symmetry for our transform function. So now we want to take our function from this form, where we could look at our vertex and pluck it right out very quickly, and put it into polynomial form. And it's always good to review squaring binomials, because sometimes we can get into trouble when we square binomials. So it never hurts to review that. So let's take a look at that. So g of x equals, so I'm going to square x minus 1 first, x squared minus 2x plus 1. Now I'm going to double everything. 2x squared minus 4x plus 2, take away 3. That equals 2x squared minus 4x minus 1. So this is the same function in two different forms. Okay. This we call the polynomial form. And this one we haven't given a name to yet, but we will when we start our demo. So that's the preview exercises for lesson number 20.